Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today we're doing a deep dive into something absolutely core to engineering analysis. It's the state of equilibrium in thermodynamics.
That's right. Most engineering design, pretty much everything from, say, simple heat exchangers right up to complex phase change systems, it all hinges on this assumption, the assumption of equilibrium thermodynamics. It basically defines the best possible outcome, the ideal state.
But, and this is the kicker, the real world is, well, it's messy. It's always running away from this ideal state. And that's where it gets really interesting, doesn't it? The actual effect of making this ideal assumption. Because a lot of crucial processes, think combustion, for example, they happen so fast, way too fast to actually hit that ideal stable state.
Exactly. And that's the context here, really. It's about the consequences of not reaching equilibrium. Things like pollutants, carbon monoxide, text canvas to Juro, oxides of nitrogen, text DOS. They are fundamentally a direct result of the system just not having enough time, not enough time to reach thermodynamic equilibrium. So before we can figure out why our real fast systems aren't getting there, we really need to define that ideal state mathematically.
Okay, so let's build up some intuition first. Before diving straight into the heavy math, the concept of equilibrium. It's often easier to grasp with simple mechanical systems. The classic marble analogies.
Yeah, those are great. They really set the stage for the more rigorous mathematical criteria we'll need later, especially when we talk about entropy and energy.
Right, so starting with the first one, stable equilibrium. Just picture a marble sitting right at the bottom of a smooth bowl. If you give it a little nudge, what happens? It rolls right back down to the bottom. It wants to be there.
And mathematically, this stability translates to two conditions. For an isolated system, the total variation of entropy, which we write as text Tau, well, that has to be negative, so text dollar. And at the same time, the corresponding variation of energy, text, has to be positive. Essentially, if you disturb it, the system's energy goes up slightly, and that pushes it back towards the stable, lower energy state.
Makes sense. Then you've got neutral equilibrium. Think of the marble, but this time it's in a perfectly flat, horizontal trough. The source material tells us it's in equilibrium anywhere along that trough axis.
Which means the criteria are zero for both variations in that direction. So text dollar is me, but only along the trough axis, of course.
Okay. Next up, 3, unstable equilibrium. This is like trying to balance that marble right on the very top point of a smooth hill or dome.
Right, precarious. And the math shows the opposite signs compared to stable. Here, text dillars and any tiny movement, any nudge at all, and it just rolls further away from that supposed equilibrium point. It doesn't return.
And finally, there's 4, metastable equilibrium. This one's a bit more subtle. Imagine the marble is sitting in a little dip, but that dip is actually higher up than another deeper dip nearby, like the higher of 2 troughs. Tiny disturbances, it just rolls back to the bottom of its little dip.
Exactly. Infinitesimal variations cause it to return, but if you give it a bigger push,
What larger variations?
you can get knocked over the edge and fall down into the lower, more fundamentally stable trough.
Okay, these analogies are helpful. Now, you mentioned the notation textagonal. Why the A? Why not just...
Good question. It's a crucial detail, actually. When we talk about equilibrium conditions, often the first order change, the differential text might be 0. That tells you you're at an equilibrium point, maybe stable, maybe unstable, maybe neutral. But for stability, you need to look beyond the first term. Text represents the total variation, which includes higher order terms from like a Taylor series expansion. So mathematically, text plus frac 2 plus whole thing, text 2 was not 0, usually, because those second derivative terms and so on are not 0. That's why, for a truly stable state, the requirement is that the total variation of entropy must be negative. It accounts for the curvature, if you like, not just the slope.
Okay, I get it. So text dollar finds the peaks and valleys, but text dollar confirms it's definitely a valley, a stable point.
Precisely. Hassavoulas and Keenan summarize the derived criteria nicely. Stable equilibrium has EDS, neutral has EDSE, and unstable has EDS, and unstable has EDS, but the I states the EDS.
Right, and that link you made earlier, the engineer's intuition that energy rises upon disturbance in a stable mechanical system, that's mirrored by this negative variation of entropy in thermodynamics.
Yes, that's the conceptual bridge.
Okay, let's use that bridge. Let's transition now to a purely thermodynamic system, the classic example. heat transfer between two blocks.
Okay, imagine an isolated system, just two metal blocks, say, initially different temperatures, text T91 and text T2. Let's assume text T is hotter than text T2. They're connected by some conductor, so heat, an amount of energy, delta Q, is transferred from the hot block to the cold block.
Now, if we imagine this transfer happening reversibly, which is sort of an idealized process,
Infinitely slowly.
then the entropy changes for each block are defined very precisely by the equations in the source. For block 1, losing heat, text 1 frac delta T1, that's equation 1.1. And for block 2, gaining heat, plus frac delta text T1.
But of course, in reality, because text T1 is actually greater than text T2, the heat transfer is spontaneous. It's irreversible. This means the actual entropy changes are greater than the reversible case. So the inequalities apply. Text 1 frac delta text T1, which is 1.1a, and text 2 plus frac delta text T2, which is 1.2a.
Okay, so for the real irreversible process, what's the total entropy change for the whole isolated system? It's just the sum, text 1 plus text 2, right?
Exactly. And when you add the reversible components, you get the change left of frac delta text 2. We can rewrite that slightly as text delta Tm.
And since we started with text 1, text 2, and delta 2 is positive heat transfer, that whole term
Must be positive. The total entropy of the isolated system increases during this spontaneous process. That's the second law in action.
It confirms the system naturally moves towards increasing entropy. Now, how do we prove that the equilibrium state itself corresponds to the maximum possible entropy?
We can use a sort of proof by contradiction. Imagine the blocks are already in equilibrium, so 2 of T equals T2 equals T. Now suppose, hypothetically, a tiny amount of heat, delta Q, spontaneously transferred reversibly due to some infinitesimal fluctuation delta T. Say, from T plus delta T to T delta F.
Okay, following the math in the source, the entropy change state would be the heat out over the slightly higher temp plus the heat in over the slightly lower temp. So text delta T plus delta delta T.
Right, and if you combine those fractions and approximate for small delta T, ignoring the tiny delta T2 term in the denominator,
you get equation 1.4 from the text. Take 2 plus delta T plus delta T plus delta T fax take delta TT. And
hold on. There seems to be a sign discrepancy in the source text equation 1.4 derivation step. Let's reevaluate frac delta T plus frac delta T plus frac delta T. Common denominator is D plus delta T to T, T to T delta T to 2. Numerator becomes delta Q delta T plus delta Q plus delta Q plus delta T. So frac and TQ delta T delta T. So approximate for small delta T. This is approx frac to Q delta T2.
Okay. The source material's intermediate step had a sign flip, but the ultimate conclusion is what matters. If we assume heat delta Q flows from hotter, delta T plus delta T2, then delta Q and delta T are both positive.
And the text would be positive, frac to T2 delta T2, delta T2, which supports the idea that any spontaneous fluctuation away from uniform temperature increases entropy, implying the uniform state was not the maximum.
Wait. The outline says the result proves maximum entropy IS obtained when T1, T2, because entropy would have decreased. Let's reconsider the source's intent with equation 1.4, even with the apparent sign issue in the intermediate step. Deprox frac 2 delta delta takes you.
Okay, let's follow the source text final form, text frac 2 delta T2. If E delta Q spontaneously flows from the slightly hotter part, T plus delta T, to the slightly cooler part, then delta Q is positive. Heat leaving the plus dt part, entering the eng dt part, and delta T is positive. In this scenario, the source's equation yields a negative text.
So, a spontaneous fluctuation away from equilibrium, uniform T, would lead to a decrease in entropy according to this equation. That doesn't seem right based on the second law.
Agreed. The derivation seems problematic as transcribed or interpreted. However, the conclusion drawn from it in the broader thermodynamic context is sound. The state of uniform temperature, T null or T22, is the state of maximum entropy for this isolated system. Any spontaneous process drives the system towards this state, increasing total entropy until the maximum is reached at equilibrium.
Right. Let's perhaps rely on the established principle rather than getting bogged down in that specific derivation's potential issue. The takeaway is clear. Equilibrium in an isolated system means maximum entropy.
Yes. And this leads to the general criterion stated by Keenan back in 1963. For stability of any system, the variation of entropy shall be negative.
Which is written mathematically using that total variation notation again as text total later. That's equation 1.5.
And this really gives us the definitive mathematical statements for equilibrium and stability in an isolated system based on entropy. If it means a spontaneous change will occur, you're not stable, maybe unstable.
Moving away from equilibrium.
2. If E, S, E, E, it means you are at an equilibrium point. could be stable, neutral, or unstable.
You're at a flat spot, peak, or valley.
And if E checks EEE, that's the rigorous criterion confirming it's a stable equilibrium.
The bottom of the valley.
Okay.
So the entropy criterion is powerful. It's universal for isolated systems.
Mm-hmm.
But it's a bit abstract, isn't it? Like, engineers usually deal with systems that aren't perfectly isolated. They're often held at constant temperature or constant pressure or constant volume.
Exactly. And that's why we develop derived properties. Things like Helmholtz and Gibbs energies. They essentially translate that abstract entropy criterion into something more tangible, often related to work potential, under those more practical constraints.
Right, making it more directly useful for design calculations.
Let's start with Helmholtz energy, which we usually denote as $5.
Okay, what's the setup for deriving that?
Imagine you have your system, System A. It can exchange heat delta Q dollars and do work delta Q.
Sure.
The first law for just System A is pretty standard. Delta text to del plus delta text Q. That's equation 1.6. E here is the total energy of the system.
Okay.
Now imagine this system interacts with a large heat reservoir at a constant temperature, $2. We want to find the maximum possible network we can get out of this combined setup, maybe using a reversible engine between A and the reservoir. Through a derivation involving the entropy changes of both the system and the reservoir, and applying the second law, we find something really neat. The maximum network obtainable, delta W text net, turns out to be equal to the decrease in a specific state function of the system A.
And that state function is?
It's ET dollars S do Y, where E is the system's total energy, S is its entropy, and T dollars is the reservoir temperature. So the equation is delta text delta stellar.
Yeah.
Oh.
Okay, so the maximum work you can extract is equal to the drop in this specific combination of properties.
Precisely. And that combination, ETSC, evaluated the system's temperature T, often assumed equal to T dollars for processes occurring at the reservoir temperature, is what we define as the Helmholtz free energy. F, for typical thermodynamic systems where the total energy E is primarily internal energy, U, the definition becomes, V dollars equals UTSC. That's equation 1.11.
So F represents the maximum total work you can get from the system during a process at constant temperature T.
Yes. And that TT dollar term, you can think of it as the energy that's unavailable for work because it's associated with the system's entropy, the energy that must be sort of discarded as heat to the surroundings to satisfy the second law.
Okay, that makes sense, maximum total work. But often, especially in like chemical engineering or processes open to the atmosphere, we care more about the useful work, right? The work that's left after accounting for pushing the atmosphere out of the way.
Exactly. If the system changes volume by text T against a constant external pressure, two-bell rule, like atmospheric pressure, it does work equal to $2 text to just on the surroundings. That's not usually considered useful.
So we need to subtract that from the network. The useful work, delta W, would be delta W delta W, which is U. That's equation 1.12.
Right. And now substitute our expression for delta W or text net from before.
Okay, so delta text U text U. How does it simplify?
Well, if the process happens at constant pressure P dollars, we can bring P dollars inside the differential as DT del. So delta text U do, combining the terms inside the differential gives delta text U E plus P0 VT0 des.
And E plus PVD is just enthalpy H, assuming E is mainly U.
Exactly. So assuming E prox U do and the process occurs at T prox T U and P prox P U, the maximum useful work becomes delta text U we text dV.
And there it is. That TTC must be the Gibbs free energy, G.
That's the one defined as DG equals HTS equation 1.14.
So G represents the maximum useful work obtainable from a system during a process at constant temperature and pressure.
Correct. And these functions, UH, F, and G, are incredibly powerful because they lead to a set of fundamental differential relations that connect all the key properties, especially when you include composition changes in multi-component systems.
Ah, the Gibbs equations. Yeah, those are central.
They are. They define how UH, F, and G change infinitesimally based on changes in T, SP, V, and the amount of each chemical species, in other dollars. Let's transcribe them from the source, including the chemical potential term Ni. Text FPP plus some me text P plus some me text T, and the really key one for many applications, text T plus V text T. That's equation 1.15.
Wow, okay. That last one, the text equation, you can immediately see why it's so useful. If you're holding temperature constant, text D dollars. If you're holding pressure constant, text Steelers.
Right. Those first two terms just vanish under those common laboratory or industrial conditions.
Leaving just text MUI text beta for a process at constant T and P, that simplifies things enormously.
It absolutely does. And it leads directly to the practical criteria for equilibrium using these derived properties.
So let's summarize those. For Helmholtz energy, F, which is useful
when volume and temperature are held constant, like reactions in a rigid thermostatic container.
Okay, in that case, the system will spontaneously change in a way that decreases F until it reaches a minimum value. That minimum F signifies equilibrium.
And the criterion for stability at constant V and T is that any small perturbation must increase F. So mathematically, text indation for stability against small changes away from equilibrium. Though the source notes text dAT$Z would be the more rigorous total variation criterion.
Got it. Minimum F at equilibrium for constant V, T. Now, for the more common case Gibbs energy G, this applies when?
When pressure and temperature are held constant, think of reactions in an open beaker or processes and flow systems at steady conditions.
Right. And the criteria here are directly analogous to the entropy criteria, but flipped because G tends to a minimum, not a maximum.
Exactly. The source lays it out clearly. 1. If text AG, the change is spontaneous, the reaction or process will proceed as written.
Moving towards equilibrium.
If text EG, the system is at equilibrium. No net tendency to change.
The bottom of the Gibbs energy valley.
And for stability, the total variation must be positive. If text $, and any fluctuation away from equilibrium must increase G.
Okay. So minimum G signifies stable equilibrium at constant P and T. Let's connect this back to the real world. Where do we actually encounter these different types of equilibrium?
Well, stable equilibrium is what we aim for in what's often called thermostatics. It's the most common state we analyze. Think about a simple mixture of liquid water and water vapor coexisting in a closed container at a fixed temperature and the corresponding saturation pressure. That's stable. Or, basically any point defined on a standard text heat PV diagram for a pure substance represents a state of stable equilibrium.
Right. What about metastable equilibrium? Where does that pop up?
Oh, all over the place, especially in systems that rely on an initiation step. We mentioned combustion and spark ignition engines earlier. The fuel-air mixture before the spark is metastable. It's reasonably stable, won't just ignite on its own, but a small perturbation, the spark energy pushes it over the activation barrier into a much more stable state, the combustion products.
Like the marble in the higher trough needing a nudge?
Exactly. Another classic example is the Wilson cloud chamber. You have water vapor that's supersaturated, cooled below its normal dew point without condensing. It's metastable. It stays as vapor until a charged particle passes through, creating ions that act as nucleation, cites the perturbation, causing condensation trails.
Fascinating. And unstable equilibrium, is that something we can actually observe?
Not really sustained, no.
Yeah.
It's inherently transitory. It represents states the system passes through on its way to a stable or metastable state. Think about gases mixing. If you have two different gases separated by a partition and you suddenly remove the partition, the initial state of separated gases is unstable with respect to the mixed state. The driving force for mixing is the difference in chemical potential, pushing the system towards the more stable, higher entropy mixed state.
Or back to combustion, the gases in the cylinder during the very rapid combustion process itself. They haven't fully reacted yet.
Precisely. They are in highly unstable intermediate states, rapidly moving towards the more stable equilibrium products like text CO2, text O. But, as we said, they might not get all the way there if the process is too fast, leaving things like text TO day.
Which brings us back to that Gibbs energy minimum at constant P and T. Why is that so critical, especially for mixtures? Engineers sometimes struggle with visualizing changes at constant P and T, causing a property like G to change.
It's because the composition can change. Even if P and T are fixed, the system isn't necessarily stuck. Take text CO2 at high temperature and atmospheric pressure. It's not perfectly stable. It can break down, dissociate into text TO and text O2 too. That reaction involves changes in the amounts, the text Q of species. According to the text equation at constant P and T, if the current mixture composition doesn't correspond to the minimum possible value of G for that P and T, then text U will be negative for the dissociation reaction, and it will proceed spontaneously until that minimum G is reached. The chemical potentials drive the change.
So minimum G dictates the equilibrium composition of a mixture at a given P and T.
Exactly. It's fundamental for chemical equilibrium calculations.
Okay, let's try and synthesize this. This deep dive has really laid out the bedrock criteria for stability in thermodynamics.
Yeah, we started with the universal tendency of isolated systems towards maximum entropy, mathematically captured by 9 text at ES, or simply D text ELA driving spontaneous change towards equilibrium.
And then we saw how derived functions, Helmholtz energy F and Gibbs energy G translate this for more practical scenarios.
Right. F defines the maximum total work available at constant V and T, and its minimum signifies equilibrium under those conditions.
While G defines the maximum useful work at constant P and T, and its minimum signifies equilibrium there, which is crucial for chemical reactions and phase changes.
The minimum energy maximum entropy principles are the guiding forces.
Now, our source material dangled a rather interesting thought at the end. It hinted that irreversible thermodynamics might be key for future energy tech.
Yeah, things like efficient solar energy conversion or fuel cells. These systems often operate in a steady state, not true stable equilibrium. They have continuous flows of energy and matter. Understanding the thermodynamics of these non-equilibrium states might unlock new efficiencies.
And it leaves us, the design junkies listening, with a really provocative question, doesn't it?
I think so. If we know that pollutants like TeX-NOx form because combustion is too fast to reach the minimum G equilibrium state, then maybe the focus shouldn't just be on the equilibrium endpoint itself. Maybe the real engineering challenge is controlling the rate of approach to equilibrium. Understanding and manipulating the kinetics, how fast the system travels along the path from its initial unstable or metastable state towards the stable one. If we could control that rate, manage that distance from equilibrium effectively, could that be the key to actually achieving near zero emissions?
Controlling the journey, not just the destination. That definitely sounds like a topic for another deep dive, non-equilibrium thermodynamics and kinetics.
Absolutely. It's where a lot of cutting-edge research is happening.
Until the next equation, design junkies, we are mechanical engineering made simple.